Hello everyone. Before diving into today's topic, we want to take a moment to thank you for your support. Every like, comment, and subscription truly makes a difference and helps this channel grow. If you enjoy our content and don't want to miss future videos, subscribe to the channel and activate the bell to receive all notifications. Now, imagine for a moment that you are standing on a vast beach, with the ocean stretching endlessly before you. The waves crashing regularly on the shore seem to originate from a distant source, from an initial beat that has propagated without end. And what if I told you that our universe might be exactly like that? A gigantic cosmic wave generated not by an absolute birth but by a bounce. An echo not from the beginning of time, but from within something even greater, a black hole. The idea may sound like science fiction, but it is gaining more and more attention in the world of theoretical cosmology. After all, the Big Bang Theory, though well supported by observational evidence, still has many unanswered questions. For example, it doesn't truly describe what happened at time zero. When scientists push the equations of general relativity to that limit, they encounter an insurmountable barrier, the singularity. A region where density, temperature, and energy become infinite, and the laws of physics cease to apply. But there's a fundamental issue with this image. It relies only on one of the two great pillars of modern physics, general relativity. When we try to combine this theory with the other major player, quantum mechanics, things change. Some scientists suggest that the singularity, far from being an inevitable point, might not exist at all. In fact, it could be replaced by a much more interesting phenomenon, a bounce. A recent, fascinating and bold study proposes a hypothesis rooted precisely in this vision. According to this model, the universe we inhabit was not born from nothing, but is the result of a gravitational collapse that occurred in a larger universe. A collapse that, instead of leading to destruction, generated a black hole. But not just any black hole. One so vast that it contains, within it, an entire universe. Ours. Seen from the outside, this gigantic entity would be indistinguishable from a regular black hole. But inside, for an observer like us, reality would appear completely different. It would appear as an expanding universe, just like the one we observe through our telescopes. The core of this proposal lies in a quantum phenomenon known as the Pauli exclusion principle. According to this principle, two identical particles called fermions cannot occupy the same quantum state. It's a fundamental rule of nature that, in extreme contexts, can have surprising effects. When matter is compressed beyond certain limits, the exclusion principle comes into play and creates a kind of quantum pressure that resists contraction. In this way, it prevents density from reaching infinite values and triggers, at a certain point, a bounce. Thus, at the heart of the black hole, instead of a singularity, a new phase is formed, a rapid expansion of matter and energy that gives birth to a universe. And this universe, at least according to the author's calculations, could be very much like our own. But the most extraordinary aspect is that this model, dubbed the black hole universe, manages to explain some of the greatest mysteries of cosmology without introducing new exotic entities. There's no need to hypothesize a mysterious inflation field or an enigmatic dark energy. Both of these elements, fundamental in the Standard Model, naturally emerge as consequences of the bounce physics. Inflation, that extremely rapid expansion believed to have occurred right after the Big Bang, is here reinterpreted as the natural development of the bounce within the black hole. And the second phase of cosmic acceleration, the one we're observing today and attribute to dark energy, would be linked to the total mass of the black hole housing our universe. In other words, the dark energy that so perplexes us could simply be a geometric manifestation, a consequence of the fact that we are inside a closed and curved system, the interior of a gigantic black hole. The small but non-zero value of dark energy would no longer be a mystery, but a direct prediction of the mass of our cosmic container. And here things get even more intriguing. Because if this model is correct, it leaves behind an observable signature, a hidden clue in the fabric of space. According to the black hole universe theory, the space we inhabit should have a slight positive curvature. In simple terms, the three-dimensional space of the universe should be similar to the surface of a sphere. We can't see it with our eyes, but we can measure its effects. Just as an observer on Earth might believe the world is flat simply because they observed too small a portion of its surface, we too might not notice the universe's curvature if it is gentle enough. But with increasingly sophisticated instruments, we might one day detect this curvature and, in doing so, provide indirect evidence of the model's validity. Meanwhile, some recent cosmological observations have already begun to show small anomalies, faint signals that seem to suggest a positive curvature of space. Nothing conclusive, of course, but enough to prompt many researchers to take a closer look at this fascinating paradigm. If these early hints were to be confirmed, we would face a conceptual revolution as profound as the transition from geocentric to heliocentric cosmology. The universe we know, with its galaxies, its physical laws, its accelerated expansion, and even time itself, would be nothing but a local phenomenon, a sort of internal event, occurring within the broader, invisible structure of a black hole. A fold in space-time that hides, within it, a completely new origin story. But what, then, lies outside our universe? What does this hypothetical parent universe contain? The model doesn't provide definitive answers, but suggests that it could be populated by many other black holes, each potentially containing its own universe. This scenario closely resembles the ideas of Lee Smolin and his theory of cosmic natural selection. Every black hole could be a kind of cosmic birth, a child of the universe in which it formed. Universes that manage to generate more black holes would therefore have an evolutionary advantage, producing more descendants. In this vision, reality is no longer a single entity evolving through time, but a multitude of universes with different characteristics, linked together by extreme gravitational events. Our universe, with its physical constants extraordinarily suited to life, might not be the result of design, but the outcome of a long process of cosmic selection in which only certain universes survive, grow, and multiply. And if that's the case, then even the question, why do we exist in this universe, would find its answer in statistics, not in chance. This concept paves the way for new interpretations of the physical laws themselves. For centuries, we've believed that the laws of nature are unique, universal, and immutable. But if each universe is born with its own configuration, then these laws could be variable, selected precisely for their ability to allow the formation of complex structures, stars, planets, and life. We would not be privileged observers, but the inevitable result of a blind cosmic process, of a selective pressure inscribed in the deepest rules of gravity and quantum mechanics. The beauty of all this is that we're not talking about pure philosophy or science fiction. The black hole universe model, bold as it is, does not rely on exotic elements. Everything it proposes arises from a clever yet orthodox use of the two great physical theories, general relativity and quantum mechanics. No unknown particles, no mysterious fields, no new physics to postulate. Just a different way of putting together what we already know. And this may be its greatest strength. In an era where many speculative theories rely on unverifiable elements, this model proposes a testable hypothesis. Positive curvature, the connection between dark energy and black hole mass, the possibility of a quantum bounce. All elements that can be tested with increasingly precise observations of the cosmic microwave background, large-scale structures, and cosmological parameters. Of course, many open questions remain. How does matter behave during the bounce? What role do quantum gravitational effects, which are still not fully understood, play? What is the nature of the parent universe, and can a metaphysics of the multiverse exist without falling into unfalsifiability? Huge questions, challenging not only science but also our intuition. Yet it is precisely this tension between what we can know and what we can only imagine that makes cosmology one of the most fascinating fields of human thought. Looking at the sky today doesn't just mean contemplating distant stars, but trying to understand if we are truly inside a larger structure, a cosmos within the cosmos, a universe born from another universe. And if it's true that we live inside a black hole, then perhaps every distant galaxy we observe could in turn hide a new reality, a new universe ready to be born. In a way, we are like fish in a boundless ocean, unaware of the lands that stretch beyond the horizon of the waters. But now, thanks to models like this, we can begin to imagine what lies beyond. And who knows, maybe one day, with more advanced instruments and even more visionary minds, we will be able to cross that boundary and discover that what we believed to be the beginning was only a passage. A gateway through which the universe breathed, bounced, and began expanding again, giving life to everything we know.